Now we introduce a artificial process named polytropic process, and this is a completely artificial process. If you don't have any knowledge about this process, you can solve all the problems. But we introduce it to create easiness of quantifying the work in expanding boundaries cases. Now we consider that there is a piston cylinder assembly as shown in this slide, that it compresses or it expands from position 2 to position 1. When it expands, and it is being compressed from position 1 to position 2. And during this process, obviously, if we assume that there's some mass of compressible liquid in this cylinder, and during this compression the pressure raises from P1 to P2. Here's P1 and P2, and if you release this system, it will expand from position 2 to position 1, and during this there will be pressure drops from P to P1. Either way, at the instant 1 we have P1 and V1, and at instant 2 we have P2 and V2 as pressure and volumes. So we have two well-defined states where we know the system's pressure and volume at both states. So both states are well defined because we know two thermodynamic properties at both of the states. Now, if we look into this work, work is for expanding boundaries. It's PdV, pressure into change in volume. How much volume change during this process is and if we multiply this change in volume into pressure, instantaneous pressure. So we are talking about a continuous process that if we drive this in certain infinite number of small portions, and then we talk about this change in differential volume uh, during an instant, and we multiply it with the instantaneous pressure, we come to know the differential work, and if we integrate from T1 to T2 during this process, we can find the work from 1 to 2. So this is the main idea, and if we and we already know that the differential is integral is the area under the curve. So if we calculate the area under this curve, this area under this curve, we will come to know the work done during this process. So but in most of the cases it is very difficult to find areas under the curve again and again, and to quantify the work. So we introduce a polytropic process. Here we also need to consider that work is path dependent. How path dependent? And if we consider three cases in which we have one state, and let me this, and another state 2. This is state 1, and this is state 2. We may have infinite number of possibilities of achieving these two states, and infinite number of processes that may occur and take system from state 1 to state 2, because states are defined using thermodynamic properties at that instant. For example, at T1 the system was at state 1, and at T2 the system was at state 2. And now system may go from state 1 state 2, adopting infinitely large number of possible scenarios. It may go like, for instance, it may go from state 1 to this intermediate state, and during this I'm gonna name it as 1 prime, and then from 1 prime to 2, and it will reach the exact same state 2 as being achieved during the process C, or if we talk about process B, we will come at the same state 2, during the process from going from 1 to 1 prime and from 1 prime to 2. And you can see that area under the curve for this process is entirely different from other three cases. If we go from state 1 to state 2 adopting curve A, path A, or path B, or if we use path C. So in both, in all of these cases, the work being done or being produced by the system is different. Now we have three. Let us draw over here that we have state 2, state 1, and the system goes linearly from this point to this point. It may choose another path. Let me draw over here, and the same two states. As let the pressure vary with respect to volume. This is V and this is pressure. Using another path, let us name as B, path A, and let us take another scenario. Now system goes like this. It is path C, and let us talk about the one we just introduced in last slide. So if we calculate the curve, if we calculate the area under the curve for these scenarios, we will come to know that in each case the value of work is different, because you can see that in each case 1, 2, 3, 4, all of these three have different areas under the curve, and because it is pressure into volume curve, so pressure into volume, if we integrate it, it will give us the work. So system can go from state 1 to state 2, state 1 to state 2, and can achieve the same states, but it can produce different work, or we have to put in work a different amount of work in each case. So we will come to know that the work is path dependent, and the quantity of work we have to put in, or we will get out of the system, depends entirely on the behavior of the system, that how pressure is being changed with respect to volume. So this concludes that work for expanding boundary cases is path dependent. the path that a system adopts to go from state 1 to state 2. Here we introduce a process name as polytropic process. It is entirely artificial process, and as I already said that you can compute everything if you don't know anything about polytropic process. We just introduced polytropic process to create easiness for our calculations. So if what is polytropic process? A polytropic process is a process in which if we take pressure at any state and volume at any state and take its nth power, P into V की power n is equal to constant. This product remains constant. So if we change the value of n, we will come to know that the system takes different paths during this process of going from state 1 to state 2. And we can use the formulation to, if you know the behavior of the system, that for instance pressure has a linear relation with the volume during the process of transforming from state 1 to state 2. We can use work formulation, which is being driven over here, and these are two formulas that we can use to quantify work. If we know what is the behavior, what is the relation of pressure with respect to volume, and we can calculate this. We can calculate, or we can define this value of n using our knowledge and our understanding of thermodynamics, and and combining it with the engineering application we are talking about. We will do some examples in which we will come to know the value of n from the statement, from the scenario we are talking about. We will do some examples in coming slides. And here there are two different formulas where if we have this n is equal to 1, then we can use this formula which I highlighted in yellow. And if the power the value of n is anything but 1, then we can use this formula. So we can use these two formulas to quantify the work depending upon what is the relationship of pressure and volume during the process.